It's important to record my pre-class announcements here too. Thank you. So chapter 23 will be covered. We'll not have a graded assignment. Dr. Baker put up some bonus homework problems there, I think, for you to look at, practice with. Final exams 2 weeks from yesterday, and SEIs are now active. So please do that right away. I think you do it for both the lecture and the recitation. So make sure to do both of those things. Questions, comments before we jump in today? No. Okay, so yes, talking about chapter 23 here. Remember we're talking about looking at how to analyze data that consists of two categorical variables. It's a thing called the chi-square test. So remember our framework here. We've looked at two-way tables a lot before. Now we want to say something about these variables overall. So say something about an overall comparison of these variables. Specifically, our hypotheses are going to be the null says that there is no relationship between the variables. The alternative says there is some relationship. So we're not saying, the alternative is not telling us what that relationship is. It's just trying to say, are they independent or are they not? So as usual, when we calculate our test statistic and everything, assuming the null is true. So here, no relationship means independent. So if we assume independence, then the expected counts in each of our cells, we can find what those expected counts are by taking the row total times the column total and divide it by the table total. So just doing a brief review here, we'll jump back into page 10 on your notes here in just a second. And then to remind you, our test statistic is this thing here. So for each of our cells, we can calculate the observed count minus the expected count squared divided by the expected count. And this thing is we're calling that our chi-square test statistic. And then just to remind you of our terminology here, the contribution for each cell is that thing that we're adding up over all cells. So for each cell, the contribution is the observed minus expected squared over the expected. And then we had some conditions for our chi-square test. So as usual, we want to make sure we have a random sample or at least a representative sample of our population. The small enough condition is actually sort of gone for now, and sort of wrapping that both into a large enough condition that we want to make sure that it's kind of long thing. So no more than 20% of our cells have expected counts less than 5 and have no zeros in the table. We want to make sure to not have that. So kind of your first thing to check is, are all my expected counts bigger than 5? If that's the case, then you're all set. If there is one that's less than 5, you can have a few of those, just not too many. So all this is review. So now we've talked about, for this test, we've talked about what our hypotheses are, thought about our conditions, said what our test statistic is. So the last thing we need to do is know how to find a p-value, and then we're off to the races with our usual strategy. So thinking about the distribution of our test statistic, we saw that it has, or what I'm telling you is that it has this chi-square distribution, which depends on its degrees of freedom. Calculate our degrees of freedom like this. And then, we've looked a lot at the z distribution, the t distribution. Those are nice, symmetric, bell-shaped things. Chi-square distributions look a little different now. So they're only positive. They can only take on positive values. They're right skewed. And again, yes, it depends on the degrees of freedom to tell you exactly which curve you're looking at there. So for any example, we can calculate our degrees of freedom. So kind of picking back up here on page 10 of your notes. So for our smoking habits and socioeconomic status example, we had 3 rows and 3 columns, which means that we had 4 degrees of freedom. So just take number of rows minus 1 times the number of columns minus 1, and we get 4 there. And remember that our chi-square statistic we found was 18.5. So we added up, we let technology do all that work for us, and we have the final result that's our test statistic. So a note here is that the mean of a chi-square distribution is equal to its degrees of freedom. So for the z distribution, for the t distribution, the mean of that thing was always 0. It was symmetric. It was centered right at 0. So there's a slight difference now here. For the chi-square distribution is that the mean of that distribution is equal to its degrees of freedom. So if we go back to this picture, and let's look at the degrees of freedom equal to 8. So my x-axis is not labeled here, but let's say here's 5, and let's say here's 10. The mean of this thing is going to be right here at 8. So this is going to be, that's going to be the mean of that curve. So it's not, it's right skewed, so it's not going to be right in the middle anymore. But yeah, so the mean of this curve is equal to its degrees of freedom. So just keeping that in mind. So what that means is that if the null hypothesis were true, what would we expect? What would we expect we would expect chi squared to be close to what? Anybody have an idea? If the null hypothesis is true, what would we expect our test statistic to be close to? The degrees of freedom, right. You'd expect that thing to be close to whatever its mean is. So close to its degrees of freedom. And so we can do sort of a reality check to see sort of just intuitively, is our null hypothesis correct or is it not? So for our example, remember our degrees of freedom was 4 and our chi-squared statistic was 18.5. So using only this information, would you sort of expect to reject the null hypothesis, or would you expect to fail to reject, or we're not sure? How many would go with A, we'd reject the null hypothesis? A few hands. How many don't want to reject, fail to reject the null hypothesis? Anybody not sure? Okay, well, the few of you who voted are correct. We're sort of expecting that we'll reject the null hypothesis because the test statistic we got, 18.5, is far away from the mean, which is equal to the degrees of freedom, which is 4. So if the null hypothesis were true, we would expect that chi-squared statistic to be close to 4, and here it's way bigger than that. So that's kind of your intuition would be that we'll reject the null hypothesis, and we'll say exactly how to make that decision, but that's just kind of your reality check there. Is that okay? Any question you guys can think of yet? Still okay? Okay, so again, now we know what the distribution of this test statistic is, and so we can now go to a table to help us figure out exactly what the p-value is, and that's something called table D. So if you've noticed extra tables in the back of your book, we're getting to another one of those right now. So this table is you can kind of read it like you read table C with the t distribution. Kind of has the same sort of a layout, and as before with table C, we need to know go to the right row that has the right degrees of freedom. So in your notes there, top of page 11 is the top half of this table D. And again, as we can see down along the left side over here, we have our degrees of freedom. And and still kind of the rows contain critical values. So you're gonna try to find where in there your test statistic falls to find what the p-value is. So since our degrees of freedom here is 4, we can go to the degrees of freedom equal to 4 row, and then we want to kind of find where our test statistic falls in that row. So again, we trace this over, and we get our 18.5 is between 18.47 and 20. And so you can trace that up, and we see that our p-value is then between 0.01 and 0.0005, 0.005, 0005, and 0.001. So kind of use this table just like you use table C for the t distribution, if you're doing this by hand anyway. But again, we'll use technology again. Again, we're using technology to find what the test statistic is. We don't want to do that whole thing by hand. And so just like we can find our test statistic from technology, we can also find the p-value here. So this is what JMP will spit out as far as the output goes. And I'll show you this again at the end. This is the kind of thing that you would expect to see on the final exam. So instead of having to calculate the whole test statistic and find the p-value, you'll be given output and say, can you tell me what the test statistic is and tell me what the p-value is. So there's a lot of information given to you here, a lot of things that you don't need. So it's important to maybe know what the degrees of freedom are. Don't worry about any of those things. And also we want to sort of ignore that first row. That's something that we won't be talking about. So to tell you what the test statistic is, you want to look in the Pearson row, and we see that here's our chi-squared statistic, and then the p-value. The p-value is right there. So comparing that with what we said from the table, we said that our p-value is between 0.0005 and 0.001. So there you go. That's kind of a confirmation that that was the right thing. Questions you guys have on the output or anything else? Yeah.
So you don't need to compare the p-value to an alpha. You just compare your Pearson x-squared value to your degrees of freedom.
Yeah. So do you need to compare? So we will still compare our p-value to an alpha. So that's kind of our next step. So sort of your reality check is compare the Pearson chi-square there to your degrees of freedom. That'll sort of say, is this even close to being, is the null hypothesis close to being accurate? But then we'll do our usual decision. To reject or fail to reject, we'll use the p-value, compare it to a alpha, and go from there. So yes, yeah. So that's where we're going in just 1 second here. So yes, now we want to use our p-value again to kind of finish off this example. Ray's getting ahead of the game here. To make a conclusion about this hypothesis test and state our conclusion. So again, here's our p-value. Because the p-value is how does that compare to sort of any reasonable alpha that you might have? It's going to be small. So again, if it's not stated what your alpha level is, go with 0.05. But when your p-value is this small, it sort of doesn't matter what your alpha is. It's kind of really small. So because our p-value is less than alpha equals 0.05, what are we going to do? Somebody in the back, what are we going to do? Reject or fail to reject? Reject, thank you, yes. So we're going to, because our p-value is really small, we want to reject the null hypothesis. And then we want to say exactly what that means. So if we reject the null hypothesis, that means we're instead going with the alternative. So that means there is sufficient evidence to say that there is a relationship between smoking habits and SES. So again, there is sufficient evidence to say that there is a relationship, some relationship, we don't know what it is, between smoking habits and socioeconomic status. Which, if you remember back to the first page of notes from this chapter, that's kind of what we thought would be the case earlier, right? We used our conditional probabilities and saw that the two variables were not independent, or the individual categories were not independent, and now we can say overall these two variables are dependent. There is a relationship between them. Is that okay with everybody, what we're saying here? So again, we're rejecting the null hypothesis, so then we're going with the alternative, which says that there is a relationship. Kind of formalize that in our usual interpretation here. Okay. Well, we've kind of been jumping through that example slowly, so let's do one more example to kind of walk through this one more time. And also, this is kind of like what you would expect to see on the final exam. So it'll kind of maybe step you through some things, have you do some interim calculations, and then the interpretations at the end are the important thing too. So here in this example, we're looking at college students and body piercings. And we looked at a survey of 490 undergraduate students at a state university. And each student in the sample was classified according to their class rank, so freshman, sophomore, junior, senior, and what some type of a category corresponding to their body art. So do you have piercings only, tattoos only, piercings and tattoos, or no body art? So no piercings, no tattoos. So in your notes you have there at top of page 12 is a two-way table for this data. And the question you might wonder is, do we have a relationship between class rank and body art category? So here's your two-way table. We have our class rank there on the left side. We have our body art categories there along the top, and you can see what all those totals are. So there also on page 12 you have the JMP output, which we'll come back to this. But again, just for now to note that, like we saw before, each cell lists both the count, which is the observed count. So this is the observed, and this is and then it also lists the expected counts. So you can compare that with the table that was before. Again, JMP will alphabetize those things for you, so it might put it in a different order than you have in your original table. Okay, so we'll come back to this. You can kind of start picking out things from there. So first we want to say what our hypotheses are here. So again, we have our null hypothesis and we have our alternative hypothesis. Who can help me out with the null hypothesis? Yeah, right. So our usual thing is there is no relationship and then just fill in whatever two variables you're looking at there. So here we're talking about class rank and body art category. So there is no relationship between class rank and body art category. What about the alternative hypothesis? It's the opposite of that, right? So we're saying that there is a relationship between class rank and body art category. So here in chapter 23, I think the hypotheses are a little more straightforward. So there's no symbols. You're just kind of writing it out in words now. There is no relationship, or there is a relationship. Okay, so that's good. So, I thought it was going to freeze on me. We haven't had the blue wheel of death in a while, have we? Okay, so we got our hypotheses. Now we want to think about what our conditions are. So, slightly different now. We want to think about, do we have a random sample? And then also think about our large enough condition. So what do you guys think? Do I have a random sample here? Well, it doesn't say so, right? So do I have a random sample here? It's not stated. Do you have any reason to assume that this would be a representative sample? Again, kind of hard to say, right? So it's not stated. We do know that the students are all from a certain university, right? So I guess the concern would be maybe it would be okay to make some statement about all the students at that university, but can we say something about all college students? Well, maybe not. So It's not stated that it's random, and we can't be sure that the sample is representative. So we'll give it a big proceed with caution over here. Not sure about that one. How about for my large enough? Am I okay with my large enough sample condition? So here I just need all my expected counts to be bigger than 5. So I can come back over here and look at all my expected counts. Looks like my smallest one is, here's my smallest one, which is bigger than 5. So we're all set here. So the smallest expected count is 7.09, which is bigger than 5. So large enough, we are all set. We're good to go there. Okay, so random sample, maybe not, but let's go ahead and do the calculations and see what we get, and realize that our results might sort of be limited to this university that the students are coming from. Okay, so again, you'll be given a table like I showed you before from JMP on the final exam, with maybe a few things missing. So you might have to calculate like an expected count or a cell contribution. So I wanted to kind of walk through remembering how exactly we do that. So here we want to confirm the calculation for the expected cell count and find the contribution for the senior / no body art cell. So going back to, we want to look at the senior and the no body art cell. So we want to confirm that our expected count really is 57.9694, and then also find what the contribution for that cell would be. So my expected count is equal to the row total times the column total divided by the table total. And so if you look there, the total number of seniors that we have is 115. So this is 115 times the total number of people in the no body art category, which is 247. And that's out of the 490 people we have in the table. And if you do the calculation, you will indeed get that that is 57.9694. So just remembering how we got those numbers is important. So that's confirmed there. So what about my contribution here? So my contribution, this is the part that this cell contributes to the chi-square statistic. So we take our what's our formula for the contribution for a cell? EI, right? So we have our backwards. So we have our expected minus the observed. Sorry, that's backwards. The observed minus the expected squared divided by the expected. So here we have our observed was 54.97. Divide that by our expected 56.97. And I actually did not do this before class. (54 minus 56.97) divided by 56.97. Oh, oops.
Wait, is it 56.97 or is it 57.97?
Thank you, guys. 57.97. It's a Friday, you know. All right, one more time. 54 minus 57.97 divided by 57.97. 0.27? Yeah. So this is 0.27. Okay, so that's just remembering how, that's something you might be asked to do in the final exam, is kind of remembering where those numbers come from. So we're not going to make you calculate the whole thing, but just remembering where all that comes from. So now we can find our test statistic, p-value, and conclusion. So again, going back to the table, back to the jump information. What's my test statistic going to be here? Yeah, so 29.507. So not 29.073. Make sure to pick out the right one there. So you'll see the p-values are about the same, so you'll make the same conclusion, but make sure to get the right one there. So our test statistic, our chi-squared, is 29.507. Our p-value, you can pull it out from that same row, is 0.0005. So now we can just kind of go ahead and make our conclusion, right? So our p-value is really small, so we're going to do what? Reject the null hypothesis, right? So because the p-value is less than alpha 0.05, so even though we didn't say what alpha was, we can use 0.05 again. We reject and again, what that means is that, so we're rejecting that there is no relationship, so that means that we're saying there is some relationship. There is some relationship between class rank and the body art category. So that's it. We're done. So it's a little faster now. Start using technology and kind of picking out the right information and making our usual interpretation. Questions and comments on this thing? Okay. Well, guys, we made it. We were at the end of the class here. So just a final note of a summary here. Kind of thinking about the two variable analyses that we've done over the course of this class. So very early on, back in Chapter 5, we did analysis when we had two quantitative variables. So when we had two numerical variables, our technique there was regression, linear regression. So for example, we could do something like predicting exam scores from the hours spent studying. Those types of questions we could answer. And by the way, don't forget about regression. I would almost guarantee there'll be a regression problem on the final exam. So that was our two quantitative variables. We had kind of what we were doing kind of all along in chapter 18 was looking at one quantitative variable and one categorical variable. So that was our two sample means, which is actually chapter 19. So we had our one categorical variable, which for example was ticket sales, and we could also sort of cross-analyze that with a categorical variable of which type of rock group we had, Coldplay versus the Rolling Stones, I think it was. So that was our kind of interim step, and now we've done something where we can talk about two categorical variables with the chi-squared test. So we have both of our variables are categorical, and we can do some sort of analysis there. Is that okay with everybody? Okay, well, I did want to throw this up here one more time. So again, this is the jump output, and just to remind you that The important things, the main thing down here is at the bottom. So here's this Pearson is the test statistic I want to go with, and your p-value. So I threw up the example you guys had from recitation, Dr. Baker's favorite example, I guess, with the political affiliation and support strike support. But anyway, so here you can see what your test statistic is and your p-value, and kind of if you had to calculate some expected cell counts or contributions, you'd be able to do that. Questions or comments on the output? Is that okay? So just make sure to pick out the bottom row there rather than the next to last row there. Okay, well, let me finish this off real quick.